A very good morning to all of you. From chapter D block and F block elements, we have completed all the important part, all the relevant topics related with D block series. Now, next one is F block elements. Which elements are called F block elements? The answer is very simple. When the last electron or the incoming electron makes entry in F subshell or F orbital, then the element belongs to F block. Remember, these are also called inner transition elements because these are present between D block and S block elements. And it consists of two series, like D block consists of four series: 3D, 4D, 5D and 6D. In the same manner, F block elements consist of two series. First one is 4F series and second one is 5F series. 4F series is called lanthanoids and 5F series is called actinoids. 4F series starts after lanthanum. Lanthanum is a member of 5D series, but it closely resembles the members of 4F series. The properties of lanthanum closely resembles the properties of 4F elements or 4F series elements. That's why we study lanthanum with 4F series, although it is a member of 5D. So elements which are followed after lanthanum are called lanthanoid. 14 elements total. Because you know it very well, S subshell can accommodate maximum 2 electrons. So we are having only two groups for S block, group 1 and group 2. P subshell can accommodate maximum of 6 electrons. So we are having 6 groups for P block, group 13, 14, 15, 16, 17 and 18. Similarly, D subshell can accommodate maximum of 10 electrons. That's why we are having 10 groups. For D block, group 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. In the same manner, F subshell can accommodate maximum of 14 electrons. That's why the F series consists of 14 elements. There are 14 elements in 4F series as well as in 5F series. Now, 5F series, it is also called actinoids. The elements which are followed after actinium are called actinoids. The 14 elements which are followed after actinium are called actinoids. Remember, actinium is a part of 6D series. It belongs to D block because the last electron makes entry in D subshell. But again, the properties of actinium closely resembles the properties of the elements of 5F series. That's why it is studied with 5F series elements. So there are two series for F block. One is 4F series, which is called lanthanoids, having 14 elements, and the next one is 5F series, which is called actinoids, again having 14 elements. The general electronic configuration for F block is given as N-2 F 1 to 14, N-1 D 0 to 1 and NS2. This is called ultimate shell, this is called penultimate shell and this is called anti-penultimate shell. It is 2 less than ultimate. It is 1 less than ultimate. So this is penultimate and this is called anti-penultimate shell. Because 4f is inner or 5f is inner to 5d or we can say 6d. That's why these elements are called inner transition elements. Now here 4f series. The first member is cerium, having atomic number 58, followed by praseodymium having atomic number 59, followed by neodymium atomic number 60, then we are having promethium 61, then we have samarium atomic number 62, then we have europium atomic number 63, then we have gadolinium atomic number 64, then we have terbium atomic number 65, then we have dysprosium atomic number 66, then we have holmium atomic number 67, then we have erbium atomic number 68, then we have thulium atomic number 69, then we have ytterbium atomic number 70, and last one is lutetium having atomic number 71. So these are the 14 elements of 4f series, and this is the important part for your class 12 syllabus. Now let us write the electronic configuration. Lanthanum is a member of 5d series and its atomic number is 57. So its electronic configuration can be written as 5d16s2. The last electron or the electron number 57 makes entry in 5d subshell. Till atomic number 57, the energy of 4f subshell is slightly higher than the energy of 5d subshell. That's why electron number 57 makes entry in 5d, not in 4f. But just after atomic number 57, that is we are talking about 58, 59 and so on, some changes takes place in the energy of the subshell, and energy of 4f becomes lower than energy of 5d. Till atomic number 57, energy of 4f is more than 5d. But after atomic number 57, energy of 4f becomes less than 5d. So electron number 58 will move to 4f subshell. So for the first element of 4f series having atomic number 58, symbol is Ce, cerium. Electronic configuration can be written as 4f1 5d1 6s2. There is no movement of electron from 5d to 4f. It remains with 5d. But in next case, in the next member, that is praseodymium, atomic number 59. The electron which is present in 5d also makes entry in 4f, as well as electron number 59 makes entry in 4f. So we will not have 4f2. Instead of 4f2, we are having 4f3 5d0 6s2. Now for the remaining members, electron will make entry in 4f. So for neodymium it is 4f4. For promethium it is 4f5. For samarium atomic number 62 it is 4f6. For europium atomic number 63 it becomes 4f7 5d0 6s2. I told you something about extra stability of fulfilled electronic configuration and half-filled electronic configuration. For F, we can accommodate maximum of 14 electrons. So if F contains 14 electrons, it is completely filled, it's extra stable. And if F contains 7 electrons, then it becomes half-filled, and half-filled configuration also is stable. So here we can say that electronic configuration of europium is stable because it is having 4f7. Now the next member will not lose its stability. And that's why electron number 64 in gadolinium makes entry in 5d. 4f is having 7 electrons here. So here gadolinium will be having 4f7, 5d1, 6s2. Now what happens in terbium, that is atomic number 65? Electron number 65 makes entry in 4f as well as the electron that we have shifted to 5d, so that we can have extra stable configuration for 4f. We will also move to 4f. So here we will get electronic configuration as 4f9, 5d0, 6s2. So 4f8 is not possible. 4f2 is not possible. Similarly 4f8 is not possible. Directly we are having 4f9. Now electrons will be successively filled in 4f. So for dysprosium it will be 4f10. For holmium it will be 4f11. For erbium it will be 4f12. For thulium it will be 4f13. For ytterbium it will be 4f14, 5d0, 6s2. Now F is completely filled. So for the last member, that is lutetium, the electron will make entry in 5d. So it becomes 4f14, 5d1, 6s2. 4f is completely filled. Now the next member, that is atomic number 72. Element with atomic number 72 will be a member of D block. Rather to say, it belongs to 5d series, because electron number 72 will move to 5d. Now, some important point about 4f series. Lanthanoids exhibit a principal oxidation state of +3. It is the most common oxidation state for lanthanoids. Remember, for D block, the most common oxidation state is +2. And in lanthanoids, the most common state is +3. Cerium and terbium also exhibits oxidation state of +4. Apart from +3, cerium and terbium also exhibit OS of +4. Reason is very simple. In cerium, we are having 4f1, 5d1, 6s2 as the electronic configuration. If all the 4 electrons are removed, 2 from 6s, 1 from 5d and 1 from 4f, then it will acquire the electronic configuration of noble gas. Ce+4 is having electronic configuration of noble gas. Inner shells are completely filled, providing you the electronic configuration of noble gas. That's why Ce+4 is stable. Then we have one more, that is terbium, atomic number 65, terbium. 4f9, 5d0, 6s2. If 4 electrons are removed, 2 from 6s and 2 from 4f, then we will acquire electronic configuration as 4f7, 5d0, 6s0. 4f7, half filled electronic configuration for terbium. 4f7 is stable. That's why terbium also exhibit oxidation state of +4. Then we have europium and ytterbium. Europium atomic number 63 and ytterbium atomic number 70. Europium and ytterbium also exhibit oxidation state of +2. See, they will exhibit +3. But with +3, they will also exhibit +2 oxidation state. Reason is very simple. Europium, by losing 2 electrons, will acquire electronic configuration as 4f7, 5d0, 6s0. Again, 4f is having 7 electrons. Half filled electronic configuration, which is stable for europium. Then we have ytterbium. Configuration is 4f14, 5d0, 6s2. If 2 electrons are removed from 6s, ytterbium will acquire electronic configuration as 4f14, 5d0, 6s0. F is completely filled. Because F is completely filled, it becomes stable in nature. That's why That's why europium and ytterbium exhibit OS of +2 also. Then about their color and paramagnetic behavior. Ions or the elements, if contains unpaired electrons, then they will be slightly attracted towards the magnetic field. If these are attracted, they are called paramagnetic substance, paramagnetic elements or ions. So due to presence of unpaired electrons in F subshell, the elements or the ions exhibit paramagnetic behavior. Also they exhibit color property. The ions are colored in solid as well as aqueous state. The reason is very simple. They contain unpaired electrons which can show FF transition by absorbing energy from the visible region. And if energy is absorbed from the visible region, then the ion will definitely exhibit color property. So it is all about the general introduction of F-block elements. Tomorrow we will start with the most important topic of this chapter, that is lanthanoid contraction. That's all for today. Thank you. Have a good day.